All right, guys, so we are the home stretch for Organic Chemistry 1. We are currently getting into Chapter 9, which is all about NMR. So something that this NMR does, you'll learn about it in physics. I'm sure Jermaine will have a twinkle in his eye when he goes over it in lecture. But it's really just a giant magnet that makes the atoms vibrate and move, and what you get is signals that you're able to then interpret into a possible structure of a molecule. So for example, when we discover a new compound or we're trying to isolate a compound, we want to figure out if it's the correct structure. And in order to do that, we do NMR. So in comparison, I'm almost guarantee you're going to get a question, just a conceptual question comparing IR and NMR. Remember, IR is only testing for what functional groups are present, while NMR is looking for the structure. And so one of the first things that you're going to get the hang of is counting signals. Most commonly, it's going to be like this: H1 NMR or carbon. So in the NMR spectrum, you're only going to see protons or carbons, depending on, you're gonna get into more detail. In Organic Chemistry 2, you're actually going to spend like 3 weeks on just Chapter 9 in Organic Chemistry 2. So really, don't stress too much about it. There's only going to be like, maybe a few questions on the exam about it. So if anything, again, just try to understand the underlying concepts. So for example, with counting signals, the number of unique environments. So this can be a little bit weird, but for an example, one thing you're going to want to look at is symmetry. So this molecule here, we see that there's a line of symmetry down the middle here. Now, again, don't worry, but this has nothing to do with RRS. This has nothing to do with stereochemistry. This is all to do with just a basic environments in relation to each other. So when looking at hydrogens, this guy here has a hydrogen. Okay, so because of this line of symmetry, these two hydrogens are the same signal. So when you're doing IR, you'll see this in Organic Chemistry Lab as well. These two signals will come up in the same place on the spectrum, and that is why we're considering both of these the same signal, because when you're splitting it, there is this line of symmetry, and so these two signals, because of this line of symmetry, will come up as one. So here I'm just gonna number it 1 and 1, just because they're both the same. Next one would be these two. So these two will be their own same signal. And in addition to this one, 3 and 3. So in total, there are 3 hydrogen signals. Okay. Now, to illustrate another example with this ring, you can have more than one line of symmetry. So you can have a line of symmetry here, you can have a line of symmetry here. So all of these, so if you get a benzene ring that's just the benzene ring, something you can just memorize is that you have one hydrogen signal. Because of the symmetry, all of these hydrogens are going to come up as the same thing in one carbon. Because again, just looking at the carbons, the lines of symmetry are going to make them equivalent to each other. So I guarantee you're going to get a cyclobutane, and he's going to try to throw you guys off with a little bit of stereochem. So we see that the line of symmetry here is, again, just down the middle in between the two methyl groups. So here we have hydrogens here and hydrogens here. And because of the line of symmetry, these are in the same environment. We have implied hydrogens here, which are in the same environment. 2, 2. And now these two hydrogens are where a lot of people get tripped up. A lot of people will say that these are in the same environment and will say 3, 3 when that's really not the case, because when we go back to the basics of orgo, this is a sp3 hybridized carbon, and so you're one of the hydrogens is going to be pointing in one direction, one of them is going to be pointing another. So really, one of these hydrogens is equivalent to the other in relation, and the fourth hydrogen is going to be equivalent to the same one on the other side. So again, to redraw this. So again, really the first and foremost thing to look at when it comes to counting the number of signals is symmetry. That's the first thing you want to look at. And another very common one that he throws out is another cyclic. Again, here's your line of symmetry. 0, 1, 1, 2, 2. And again, going back to this sp3, we're going to see that this is sp3, so you have a hydrogen and hydrogen here, but because there is that line of symmetry that are splitting these two at the same carbon, 3. So in total, you're going to have 3 hydrogen signals. Another one of the underlying concepts when it comes to NMR is chemical shift. So really, all of this is saying is the position on the graph or spectrum. And again, the position will tell you how what's called shielded or deshielded. When you have your NMR graph, you have two terms that you're going to want to remember. It's upfield and downfield. So if something is pointing here, unfortunately, we grow up having this as 0 and as this is whatever, 12. But unfortunately, in NMR, it's the reverse. So going this way towards the y-axis, towards the intercept, it's downfield. And if something is shifted downfield, it is deshielded. Downfield, deshielded. And if something is upfield, what it must be is shielded. Now, what this means is this has to do with the electrons that are surrounding the hydrogens. So really, how protected is it versus how unprotected is it? That's one way of thinking about it. So, for example, if we have this ethyl alcohol, so we know that this oxygen is very electronegative, and so it's going to be pulling electrons towards itself, and so that this proton, there's less electrons around it because it has this partial positive, and now this has this partial negative, because again the electrons are coming away from it, and so it's less shielded. And therefore you call it de-shielded. So this hydrogen here is de-shielded because this electronegative atom is pulling the electrons away from it. And okay, so in terms of chemical shift, you're probably going to see this in SI or another resource, but you're going to want to remember some regions, and those are going to, all of these are measured in ppm, and so like IR, something easy to remember is just these regions, and so you have ppm. You have this alkyl groups or aliphatic groups, and they're going to occur in this range. So if you have a molecule like this, just a hydrocarbon, it's all it contains is carbons and hydrogens, and so there's not anything electronegative. There's not anything electronegative that's pulling electrons away, and so that's why it is more shielded. And going back to our graph, if something is more shielded in the upfield, it's going to have a lower ppm. That's how we get this range. Going up, if you have a heteroatom, which will look like this, or like this. So if you have a heteroatom such as an alcohol, like the previous example, you can assume that you're going to have a higher ppm range. This signal is going to occur in this range. Okay, so going back to the graph, this electronegative atom is pulling electrons away from this proton, and so it has less protection, and so it's de-shielded. So again, in comparison to something that doesn't have an electronegative atom, it's going to occur more downfield. Double bonds. This is definitely something you should memorize. If something is connected to a double bond, it's going to occur in this range. Again, this is all in relation to the shielding and de-shielding. Aromatics, such as that benzene ring, is going to occur in this range of ppm. So if you have a benzene ring, you don't have to worry about what's aromatic and what's not. Just if you have a benzene ring, these hydrogens coming off of it are going to show up on this graph in this range. Okay? And that's really the extent of what you're going to have to know for a chemical shift. Okay, so another very important concept to know when it comes to NMR, and that is called multiplicity, or in other words, he may use other terms interchangeably, coupling and splitting. All this means the same thing, and what this really means is just the number of hydrogens that are adjacent to a unique environment. And the rule that we use to determine this is n plus 1. And what n equals is just the number of unique neighboring or adjacent hydrogens. So when you're given a molecule and you're asked for what is the multiplicity, for example, of a given atom, so if you're looking at a carbon, what's the multiplicity of that group? You're looking at this rule here. So for example, a very common and easy one that we could go over is one that you're probably going to see in SI, is this. So for example, just, I'm going to label these A, B, C, D. So again, we're only looking at the multiplicity of hydrogens. So here, A, I'm labeling these 3 H's. B is these 2. C is these 2. And D is the one on the OH. So to determine what's the multiplicity of A, again, we're going to use this rule. And so what are we going to look at first? We're going to find N. So how many what's the number of unique neighboring hydrogens? So all of these are in the same environment. If we go to one next over, we have another unique environment that's different from this one. So in this environment, there are 2 hydrogens. So 2 plus 1 is 3. So what you're going to find is that we have terms called that are singlet, doublet, triplet, and you're going to get into, higher order things in Orgo 2, but higher than triplet, you're really just going to just say multiplet for now. So if you have a multiplicity of 3, intuitively that must mean it's a triplet. So on the graph, again, all this relates to the spectrum that you're viewing. So A, again, is going to be a triplet. So the spikes are going to look like this. And each one of these peaks represents the hydrogens involved. So going to B, we have how many, we're looking at the unique environments coming off of B, okay? So the neighboring hydrogens and other unique environments in relation to B are these hydrogens and these hydrogens. And here there's 3 of them, and there's 2. So N is going to be, again, N is the number of neighboring unique hydrogens. And so in total, there's 5 unique neighboring hydrogens in relation to B. So the multiplicity is a 6, or a sextet. But really in Orgo 1, you're just going to call it a multiplet. And on the graph, it's going to look like this big thing like that. And so these hydrogens are going to show up on the graph like this. And so one way of thinking about it is doing the reverse. If you have a graph, each one of the peaks will tell you what the multiplicity is. And given that, you should be able to figure out what the structure may be. So again, continuing along this molecule here, looking at C, what are the neighboring unique hydrogens? Again, we're doing n+1. So what you're going to find is that we're not going to count this one because we have this big atom here that's in the way of splitting this hydrogen. So for now in this course, you're not going to split through hydrogens that are bonded to a heteroatom. So right now, in relation to C, the only neighboring unique hydrogens that we find are here, which is 2 other hydrogens. So 2 plus 1 equals 3. So 3. So C and B are both a triplet. And now finally for the OH, again, looking at this one, it's not bonded to any other carbons that contain hydrogens. So there's not going to be any unique neighboring hydrogens. So the n+1, it's just 0 plus 1. And you end up with 1, which is a singlet. And again, on the graph, remember going back to our chemical shift, something that is de-shielded is attached to a heteroatom because the heteroatom is electronegative and it's pulling the electrons away. So this atom is de-shielded, and if something's de-shielded, it's going to occur downfield, way downfield. And so this, just an example, will occur like that.